Okay. So, I hope everyone had a nice day yesterday. Some intention at least. Today, as soon as I can figure out how to use technology again. Today, we're going to continue looking at current assignments, namely the types of vector questions that you will see on the 15 through 20. Further talking about the relationships between displacement, velocity, and acceleration, and do with those things. Before we begin today, how are you guys doing? And do you have any specific questions before we get started? Anything specific from this assignment or in general? Yes?
4 through 9, I'm confused on what you mean by like, what are we converting it to? Because like the first one,
Okay.
grams, isn't it straight up grams already?
Yes, yes it is. So that is a good question. Thank you very much. I will gladly elaborate, and I apologize for the confusion. So homework 4 through 9. See if I can get the document on screen. That'll show everyone. There we go. So 4 through 9 are all about converting between metric units. And the goal for each of them is to convert everything into the base unit for that particular measure. Yes?
Can I have that?
Oh, yes, absolutely. Now, at least in the metric system, where we're constantly converting between different prefixes, every unit is considered to have a base value. And that base value is the unit itself without any prefixes. So the three things that are considered the main metric units, the three that only exist in metric, or at least famously, are excuse me, grams, which is our measure for mass, meters, which is our measure for distance, and liters, which is our measure of volume. In the imperial system, it's not actually a common American unit for mass. A lot of people just use weight, which is technically a different thing. But here in the US, we have things like feet and miles for distance, and gallons and cups, and pints and quarts for volume. And these three things are the base unit for whatever the variable in question is. So for all of these, the goal is to look at what you have, look at the actual unit and whatever prefixes are attached, and convert it into the base form, which is to say you want to remove the prefixes. So, looking at number 4 to begin with, we have 456 grams. Grams is the base unit. You're done. Now that said, I'm going based off of technical definitions here. Grams is the base unit. As a note of forewarning, physics does tend to use kilograms more often than grams. In chemistry, we work with grams typically because you're dealing with very small piles of chemicals and reagents and dust. But in physics, we use kilograms because mass tends to be, like the masses of things in the universe tend to be a lot bigger. So set everything to kilograms, so all the numbers were just a little bit smaller. But for the sake of this particular question, where we're just setting to the base unit, grams is the base unit, that's the end of this particular part. Any questions about that?
You just leave it at 456?
You can just leave it. I'd say maybe underline it to show that you have noted and marked this is the answer and didn't just leave it blank. But yes, that's the base unit. We're done there. Next, number 5. This is in milliliters, and actually to convert this to liters, we don't need to worry about this little paragraph here. I left that in by mistake. I apologize. Because the goal is just to convert milliliters to liters, the base unit. So to help with that, let's put the chart of metric prefixes back on the board. Does anyone remember the mnemonic for the initial 7 metric prefixes? That is okay.
Like the same, so like chocolate milk one or something?
Yes, the chocolate milk one. It's okay if you
So
don't.
like King Henry
Died drinking chocolate.
Correct. Which is a little morbid. I was not on the committee that came up with this, or the one for the planets that involves generous mothers and pizzas. But the mnemonic for the 7 base metric prefixes is King Henry died by, the B stands for the base unit, drinking chocolate milk. And these stand for kilo, hecta, deca, not deci, but deca with a K, base, deci, centi, and milli. And these are all spaced 10 apart. So if you were converting from base units to deca, you would drag your decimal point 1 space to the left. For this for number 5, we're starting in milliliters. We would like to get that into the base unit of liters. And a very, very simple way of just doing these conversions is if you have this little chart written out, simply take your pencil at the unit you're beginning at, milli, and simply hopscotch your way over to the unit you want to be at. Question, yes?
What is H and B and C again?
H is hecta, H-E-C-T-A. B is base, that is where the base unit lives. We call it base because every possible base unit lives here: grams, liters, milliliter, sorry, grams, liters, meters, normal seconds, etc. Whatever, if the unit lacks a prefix, it goes right here on the chart. What was the other letter you asked about?
C, chocolate.
That is centi, like centimeter. So a straightforward way for these conversions to work is if we start at milli, that's going to jump us 3 spaces to the left. So 556, we take our decimal point and we jump 1, 2, 3 spaces to the left. And that converts us to 0.456 liters. Which is to say that there's 1,000 milliliters in a liter, so the number is 1,000 times smaller. The next one I'd like to talk about because we have 2 different units to convert here. This is 78 grams per milliliter. So this one, rather than doing the hopscotch method, I would probably set up with the railroad system. So I'm going to write out 78 grams per 1 milliliter. The base unit here would be grams per liter. You want both measures in their base form. And grams is already where we want it to be, so we really just need to convert milliliters. And I like drawing out the railroad to make sure that I'm multiplying, dividing correctly. So the conversion goes 1,000 milliliters in 1 liter. And if we orient it like this, multiplying by a fraction that equals 1, so we're not changing the value, but by orienting the fraction like this, the milliliters can cancel, and that'll leave us with grams over liters. How does that make you feel? So 1,000 times 78 should be 78,000 grams per liter. And I want to at least mention 7 and 8 because they use units that are not part of the standard set of 7. They don't live in the mnemonic. So I would like to talk briefly about nanometers and megameters. We have more prefixes than just these 7. Because if we had to describe the length of the universe in terms of kilometers, the numbers would get really, really big. So we have more prefixes in both directions, but whereas with these 7, they're all spaced 10 apart, the others are spaced 1,000 apart from the ends, from whatever side they're extended from. We didn't bother naming every single multiple of 10 because there would be too many of them. So I'm going to put 1 dot between all of these to indicate that they are all times 10 apart. I'm going to put 3 dots between kilo and the next biggest one, which is a big capital M, or mega. 1 megameter is 1,000 times bigger than a kilometer, not 10 times bigger. So, nano came first, so we'll go the other direction now. So there's many more that are bigger than kilo and even bigger than mega. Similarly, there's also many that are smaller than milli. If we jump 1,000 times smaller than milli, we arrive at micro. And because we've already used the letter M too many times, we use instead the Greek letter mu, because we ran out of European alphabets a long time ago. I'm going to just label this in English beneath it, micro. The symbol is mu. It's kind of like a really fancy cursive M. And then 1,000 times smaller than micro is nano. So, looking at 7 and 8, we're initially given, Gesundheit, 578 billion, 400 million nanometers, which is a big number, but it's nanometers. So this is the unit itself is very, very, very small. So it's a big number in a small unit. We want to convert that to meters. So looking at this sort of modified table here, the jump from nano to micro is 1,000 times bigger. So that's, you move 3 decimal places to the left to go from nano to micro. Then another 3 decimal places to the left to go from micro to milli. So right now we're dragging 1,000,000 times bigger, 6 decimal places to the left. And then 3 more to go from milli to base. So we're jumping a total of 9 spaces to the left. How do you guys feel about that part so far? Okay, mostly nodding, a couple thumbs up. If you don't feel good about that, please let me know. That would put this number, we go 9 spaces from start to finish, that would put us at 578.4 normal meters. Why did I put a line there? 578.4 normal standard meters. Now, we're going to do the reverse with megameters. We have to start with 0.000005612 megameters. That is a small number in a very large unit. So, going in the reverse direction now, to jump from mega down to kilo, we want to go 1,000 times smaller. So that's going to be 3 spaces to the left, sorry, to the right this time. And then from kilo back to base, another 3. So a grand total of 6 jumps, 6 places to the right. That should put us at 1, 2, 3, 4, 5, 6. By my math, please correct me if I'm wrong, 5.612 meters. How do you guys feel? Okay. Number 9 is simply kilometers back to meters. And then 10 through 14 are about scientific notation. Does anyone have any questions about scientific notation?
What's MJ?
That would be megajoules. That's a good question. So the M is the prefix mega, so we can use this to convert that megajoules into its base form. The J is the unit, that is joules. This will come up rather frequently in physics classes. Joules is the metric unit of energy. So 67 megajoules is a lot of energy. That's a lot of donuts eaten and a lot of calories burned.
And then for 14, there's no,
Correct, there's no number, sorry, there's no unit for 14. So for 14, simply take the number as is and convert it into scientific notation. No need to worry about its unit or changing its unit.
You said don't worry about 14.
Sorry, do number 14, please do number 14, but there's no conversion necessary. We're just taking it and putting it into scientific notation. So, to represent something in scientific notation, we want to take the big, huge number and shrink it to fewer terms. So, 3, 6, 9, 10, 11. We can jump the decimal point 11 spaces to put it between the 7 and the 9. 7.93 times 10 to the 11th power. And represent the same number, ideally with fewer keystrokes.
Does scientific notation mean with the times 10 to 7?
Correct. When you convert something to scientific notation, the goal is take whatever the number is, convert it such that it is in the form number dot number number times whatever multiplier is needed to get it from its base into this form. So if we were to literally multiply 7.93 times 10 to the 11th power, that would jump the decimal point 11 spaces back to where it came from and give us the original number again. And to look at a couple more of these, for 13 we have a 0.0000005612, another number, and you can do scientific notation making 4 a number smaller than 1 as well. We would go 1, 2, 3, 4, 5, 6 decimal places to get the decimal between the 5 and the 6. So 5.612. But because we were going to the right, that's going to be times 10 to the negative 6th. The original number is smaller than 0. And so this multiplier represents that the original number is very, very small. Yes?
Do we need to include all of it, the 5612, or can we do like 5.6 times 10 to the negative 6?
The most scientifically accurate thing would be to keep the whole number, because unless you were doing an operation, like doing math that would change the number of significant figures, you keep the number you have. That is the most scientific method, rigorous thing I can recommend. Yes?
For 10 through 12, wouldn't it just be the number and then times 10 to the 1?
Yes, for all of these, if you don't convert them into their base unit, you could describe them as 6.7 times 10 megajoules. Alternatively, you could describe this as 6.7 times 10 to the 10 regular joules, but either answer is technically correct. So I will accept either form. So for this particular assignment, first 14 are, I would say, conversion questions, and then the next 5 or 6. Next 6 questions are all some type of vector algebra, which we are going to, unless there's anything else you guys have at the moment, to take some time to look at that. Because we talked about displacement and velocity, I'd like to describe acceleration a bit next, and how it's going to affect a few of these questions. I'm going to make it a little easier. To talk briefly about a few of these as we're going. Number 15, we are trying to find a total displacement. We have a starting displacement of 5 miles, then we walk 3 miles per hour for 2 more hours. Just looking at this information, this is your velocity, this is the time moved at that velocity, sorry, the time you spent moving at that velocity. What is the distance traveled just in this piece right here? A little louder, sorry.
6 miles?
6 miles, very good. 3 miles per hour for 2 miles, velocity equals distance times time, therefore we can rearrange that to get delta t equals v, sorry, delta x equals v times delta t. So 3 times 2 is 6 miles walked. So we started with 5 miles, we walked another 6 miles past that, total distance 11 miles. Now, the rest of these questions are all going to involve acceleration in some way, shape, or form. And that's a term that is within the common American English vernacular. When you are, say, driving a car and you accelerate, how would you describe what happens? You're speeding up. The goal is to change your velocity. You want to go faster. So, get up my notes. All 3 of the vectors that we have analyzed so far are all connected in some way. Displacement is simply physical distance between 2 points. Velocity is change in displacement over time. Displacement is how far you went, velocity is how fast you got there. And acceleration, whereas velocity is displacement divided by time, acceleration is change in velocity divided by time. Acceleration, by definition, is a change in how fast you are going. So when you get in a car and you hit the accelerator pedal and you speed up, say for example, a pretty common figure in the car world is the amount of time it takes to go from 0 to 60. Something that comes up a lot in car commercials, I feel. So So say you first get in your car and it's at 0 miles per hour. You hit the accelerator and some number of seconds later, you have gone up to 60 miles per hour. This is your change in velocity. You have increased your velocity from 0 to 60. And that took some amount of time. Commercials will advertise, you can go 0 to 60 in 3 seconds. You can go 0 to 60 in 2 seconds. Those two pieces of information together tell you the car's maximum acceleration. The definition of acceleration is change in velocity over change in time. Whenever you change velocity for any reason, either speeding up or slowing down, you are technically accelerating. So let's say we're looking at a car that can go from 0 to 60 in 3 seconds. Acceleration is equal to delta V over delta T. Well, these units won't match up perfectly, but it gives you an idea of where to put everything. So we divide the change in velocity, 60 minus 0 is 60, by the time, and that tells you the acceleration, the rate of change of velocity. These units don't match up. We'd have to do some converting there, but it's a good indicator of where to put everything in the formula, I think. And technically you can accelerate while slowing down, because acceleration is a vector, meaning it has to point in a direction. If you were, say, driving forwards and you started speeding up forwards, you are accelerating in that direction. You are gaining velocity in that direction. Say instead, you were driving forwards and you started slowing down. You are still accelerating, you're just accelerating that way. Does that not make sense to anybody? Saying that doesn't make sense? That's fair, that is fair. Imagine if instead of hitting the brake while you were driving, you threw it into, you're moving forwards, then you threw it into reverse and kept hitting the gas. What would happen? Besides being terrible for your clutch.
Go backwards?
You go backwards. You'd still accomplish slowing down, because if you're going forwards and accelerating backwards, your velocity will change to become more in that direction. The goal of acceleration is not go faster. The goal of acceleration is change velocity. And the direction of the acceleration vector points to what direction the velocity is changing in. We'll work some examples, because I've just been hand waving up here, kind of give you something concrete to look at. Real quick, I want to show you these again, because these formulas are going to be very handy on the next couple of the rest of the homework. We spent several problems looking at this one. This is the one we just talked about. It's the definition of acceleration. Do copy these down. They will come up momentarily. So, let's look at number 16 again real quick. Billy Bob's going to come up a lot in this assignment, is completely stopped at a red light. So, let's start listing variables together. Billy Bob is stopped at a light. That tells us at the beginning of this example, the beginning of this experiment, Billy Bob's initial velocity. Okay, good. We're in meters per second. Is 0 meters per second. No velocity, not moving at all. That is what we are doing, stopped at this red light. And then, once the light turns green, we are going to accelerate at this particular rate for a total of 1.2 minutes. So, Billy Bob's going to press the accelerator. The car will begin accelerating. It's going to begin picking up speed. And we know that the acceleration is 2 meters per second squared. We do this for a time of 1.2 minutes. And briefly, I want to look at that unit together. Does looking at this flummox anyone? It's okay if it does. I just want a general assessment of that. Because I know this is a little hard. Like looking at this the first time, it's not immediately obvious what it actually means. With meters per second, you travel X meters in X seconds. But what this represents is, if you remember how we found, the formula for acceleration, delta V over delta T, the units here are meters per second divided by seconds. This is the rate of change of velocity. We're dividing velocity by time. Again, so meters per second over seconds can be simplified to meters per second squared. Every single second, your velocity changes by some amount of meters per second. How do you guys feel so far? At least one nod, a couple inquisitive glances. That's okay. For part A, the first thing we are asked is, what is Billy Bob's final velocity? So, with these three known pieces of information and this unknown piece of information, and the formulas that we have looked at so far, do we have what we need to find final velocity?
We need to make decisions.
Very good. So we're going to continue using this formula. It has acceleration, it has delta V, and to go ahead and elaborate, delta anything is always final minus initial. So I'm going to rewrite this as velocity final minus velocity initial over time. We know A, we know T, we know VI, we can find VF. And yes, thank you for pointing out, we were given time in minutes, so we have acceleration in meters per second squared. Typically speaking, unless I tell you otherwise for some reason, our formulas are designed to take seconds per unit of time. And it's going to be easier to convert minutes into seconds than it's going to be to convert meters per second squared into meters per minute squared. So before we do any more math, let's figure out how many seconds are in 1.2 minutes. 60 seconds in 1 minute. So 1.2 times 60 is, thank you very much. Calculator is faster than my brain. 72 seconds. So, we looked at what we know, we looked at what we want, we found a formula to use, we start plugging things in. Do the work in orange now. So, for A, you plug in 2, you want VF, it's minus VI, which is 0, all that over 72 seconds. What is our final velocity in meters per second? Thank you very much. 144 meters per second. Now, that is the correct answer with all the numbers we've been given. We got there, wonderful. Brief reality check though, and it's okay if getting used to meters per second and like getting used to the concept of using meters is still adjusting in your brains. Is 144 meters per second a realistic speed to be driving on an American road in a car? No. That is somewhere between 1/3 and 1/2 the speed of sound. You would be turbo arrested. I don't know who Billy Bob is or where Billy Bob got this car, frankly, or what road he can pull this off on. A common thing that will come up in physics questions is, and this is true of ones even I write myself to give you guys, because sometimes I just don't triple check reality on all of my questions. Sometimes the problem will have a solution, you can mathematically figure it out, it just won't always make physical sense. Because a human is writing these, humans are not perfect. But for part A, with the numbers given, the answer is 144 meters per second. So then, part B, how far did Billy Bob travel? As you are accelerating in your car, say you're tracking your speedometer, you're going from 0 to 60, do you stay still while that's happening? No, you are moving forwards as you're accelerating. Similarly, if you hit the brakes and you want to go from 60 to 0, you're going to still skid forward some distance while you're slowing down. You will travel while the acceleration is happening. You don't just hit the pedal, rev up to speed while stationary, and then just go at that speed. That would break your neck. So we want to figure out how far we traveled while this was happening. Can we do that with this formula? No. Good assessment. This completely lacks a displacement term. This formula by itself cannot tell us how far we went. Which is why we must turn our attention to part 3 of the Fantastic Four. Each of these formulas serves a different purpose. The first formula, its purpose is when we are looking at displacement while moving at a constant velocity. Formula 2 is the definition of acceleration. Formula 3 tracks displacement when your velocity is not constant. Formula 3, you are looking at your change in location based upon your initial velocity and how much you're accelerating and how long you're doing both of those things. The amount of time you are performing both of those actions. A brief, minor bookkeeping note. If you see a subscript of 0 or O, that means the same thing as if I put a subscript of I for initial. Different textbooks, different authors will use each one in different specific places. I think the 0 stands for the not, N-A-U-G-H-T, which is a common American and South African term for 0 or nil. Have a good day. So, we're going to use this formula for a lot of the problems moving forwards. This formula will let us look at specifically how far we go while we accelerate. So I will write that formula down since it's not on the homework itself. We have delta x, which is to say how far we traveled, equals velocity initial times the time we are traveling, plus 1/2 times the acceleration times the time we are traveling squared. This is the same t for both of these. However long the experiment happens, it's the same time for both of those variables. And this formula might look familiar because we've used it in math samples before. We've used this formula when looking at quadratics as an example. This is where it actually comes up in physics. So, how far did Billy Bob travel? We'll use that new formula there. We want how far I traveled. That's delta x. That is what we are solving for. So we found the first thing we were looking for. I'll fill in that blank. Now we want delta x, the thing we don't know that we want. So delta x is equal to velocity initial times time. Same situation. What was the initial velocity? 0. So that whole term is just going to go away. 0 times t is 0 plus 1/2 times a times time squared. You still want time in seconds. Seconds unless I tell you otherwise. So we're going to plug in 72 and then square it. How many meters is that?
5,984.
Correct. Please by my math. Does anyone disagree? It is okay if you do. Just want to know. All right. 5,184 meters traveled in 72 seconds. That's a lot. That is, convert that to feet real quick. That's 17,000 feet, which in terms of football fields, that's 57 football fields in 1.2 minutes, while accelerating. You only reach top speed at the very end of that. Again, entirely unrealistic, but numerically correct for the numbers we've been given. Bob would be in turbo jail. Any questions about this particular iteration of Billy Bob? Yes?
So with the initial, because usually unless it gives you an initial, it will be 0, so that whole term will just cancel out.
Yes, if v initial is 0, 0 times time is 0, so that term goes away.
Is it more often 0 than it is an actual term?
It's going to depend entirely on the example. As a sample of when it isn't, if we look at 17, this is either the same Billy Bob after he escaped turbo jail, or he was never caught in the first place because he has the fastest car in the world. Billy Bob is cruising down the road at 36 meters per second, which is still too fast. And then there is a traffic light 1.2 kilometers ahead that is starting to turn red. So at the beginning of this question, Billy Bob has a non-zero starting velocity. And then Billy Bob is going to start slowing down because he wants to be at a final velocity of 0 after traveling this distance. So in that situation, the starting velocity will not be 0, but the final velocity will.
So do we have delta x in this example?
In this example, yes, we do. To continue reading the question, Billy Bob hits the brakes so that he is slowed to a stop by reaching the light. So good practice is to list all of our variables. So let's do that together looking at 17. It'll help us figure out exactly what information we can glean from each part of the question. Billy Bob's initial velocity is 32.6 meters per second. And we are told that Billy Bob is going to basically skid to a stop over a distance of 1.2 kilometers, which is very far. This is another one of those questions that doesn't match reality super well, but there is still a numerical answer. So the delta x is going to be at 1.2 kilometers. That is the distance traveled whilst slowing down. And by the time we have skid this entire distance, the car will finally be stopped at a final velocity of 0 meters per second. So that is what we are given. We are asked, first thing, what is his acceleration during this whole process? With the formulas that we've used, can we determine acceleration from these pieces of information? No. We want this formula, to find A, we would need a change in velocity and change in time. This formula, no delta x, no initial velocity, but we also still don't know time if we wanted to find A. So with what we currently have, none of the first three formulas we've talked about will give us that information. So time, the Fantastic Four Part 4, the weird one. Number 4 comes up the least out of these four equations, but it is useful in that you can track the relationship between displacement, acceleration, and velocity without needing time. There's no t in this formula. We just have the initial, the final, acceleration, and distance traveled. Suppose it's not exactly displacement, it's not necessarily delta x, but it's still distance traveled. So our delta x number can go there. It's just a difference in the authors who wrote these particular parts of the slide. I will copy this formula over here, and we will end by using it as a sample. So, looking back at the question, let's real quickly find that particular number. So, velocity final squared is 0 squared equals velocity initial squared, 36 plus 2 times A, which is what we want, times our displacement, which is 1.2 kilometers. Do you think we want to plug kilometers into this? No. So how many meters is 1.2 kilometers? Almost. Kilo to base is times 1,000. So I'm going to write the 1.2 real quick. 1, 2, 3, 1,200. How do we feel? What do we got? Go ahead and say it, even if it seems weird. Oh, I also got 5-4. Somewhere between walking the 3 steps from my calculator to this part of the board, I transposed a digit in my brain. Yes, this is our correct answer. The negative simply tells us that we are slowing down. This is a vector. If forwards is positive, slowing down and basically accelerating backwards would be negative. So that is the answer to our acceleration. Now that we know acceleration, part B says how much time did this take. We can pop that acceleration into formula 3 and help us figure out time. Alternatively, actually, it'd be simpler to use this one. It'd be simpler to use formula 2. There's no quadratic there. bit over, I apologize. Please go ahead and work on 18 over the weekend, sorry, tonight and tomorrow, excuse me. I would like to talk about 19, 20, and 21 in more detail on Friday. If it ends up being that if we just finish the homework together that day, that will ultimately be okay. Because those are about falling and projectile motion. So we're going to have to talk about gravity. So, make sure you are good on the first page. Make sure you're good on the first page. That is your out-of-class assignment. And at least glance at 19, 20, and 21. We will talk about them specifically as gravity and falling and thrown objects on Friday. Any questions as you guys are tracking up?
You said this was due on Friday?
Yes. It may be that we just finish it together and I take it up at the end. And then I will just grade it over the weekend, and you can pick it up from my office next week before next Friday. Have a great day.